structures. Now, what is inside crystal structures? That's what we're going to look at. And we're going to investigate properties of different kinds of crystalline matter. So, one class of properties are the structural properties or the elastic properties. How does an object flex when it is subject to a pressure? How does sound travel in a solid? What happens when you increase the temperature of a solid? So temperature is a very important parameter in solid state physics. Any experiment that you do, you need to find out how the properties vary as temperature, and that gives us some idea of what kind of phenomenon are there inside the solid, what kind of processes exist inside the solid. So in order to look at all these properties, we would like to see how the atoms that make up the crystalline structure respond to stresses, and how do they respond to temperatures. So in equilibrium, all the atoms are in their fixed positions, which are defined by the space group, etc. But they can also oscillate from their equilibrium positions. And when they oscillate, do keep in mind that each atom is bonded to neighboring atoms, and there are interactions between atoms. Just like you pull a string, when you pull a string, there's a restoring force that tries to bring that object back to its equilibrium position. Likewise, when you displace atoms from their equilibrium positions, there are forces that are set up inside the solid. And when there are forces, there are also accelerations. So there is an equation of motion corresponding to this giant conglomerate of atoms inside the solid. So it's the many degrees of freedom, because there could be billions and billions of atoms inside a small piece of solid. It's a very complex problem. But luckily, the periodicity helps us look at smaller units of this problem. So what we're going to explore starting today is the subject of crystal dynamics. Now we suppose that we have a lattice, and there are atoms inside the lattice, and there are unit cells, and it's a periodic structure. So we suppose we pick up a certain unit cell inside the structure. Suppose this is the origin of the unit cell. So we define some origin inside the solid, as we've already done. Let's suppose this position vector is Rn. Now this index n specifies which unit cell we're talking about inside the solid. And there are atoms inside this unit cell. Let's pick a particular atom which is at a location Ra inside this unit cell. This is the same notation that we've used when we discussed the derivation of the structure factor. Now suppose that this atom can vibrate about its equilibrium position, and suppose the displacement is some other vector. Let's call that vector S. Since it's in the nth unit cell, let's identify it as SNA. Okay? So this is our scheme. Now when there are multiple n's, so n can be a very large number, A is an index that runs over the number of atoms that exist inside the unit cell, and S is some displacement, and all of this could be three-dimensional. These vectors could be three-dimensional. Then as these atoms oscillate, The atoms in the case of an insulator, they are neutral, but in the case of a metal, they are positively charged because you have a sea of electrons, the valence electrons have been stripped out. So these could be ions for ionic crystals, they could be atoms for for other kind of covalent crystals. So, but these ions or atoms are massive as compared to the electrons. Okay, so when these atoms oscillate, the overall energy changes because when you displace an atom from its equilibrium position, the energy goes up, as we all know. The electrons, however, in this problem, they are ignored for the time being. And we assume that the electrons are very light, so whenever these nuclei or cores, they oscillate, they create a new potential and the electrons immediately readjust to that new potential. So the electrons are always in the ground state. But the atom or the crystal itself will have some energy. Suppose that energy is U. Okay. Now, and the atom itself undergoes some displacement S. Since this S is the displacement of an atom A inside the basis which belongs to the nth unit cell, we call this displacement SNA. Now all the atoms inside the crystal can be displaced from their equilibrium positions, and SNA shows the displacement of each atom from its equilibrium position. Now this displacement, when everything is in its equilibrium, there has to be some ground state, but when the displacement from the equilibrium happens, the energy goes up. So if you look at the internal energy of this system U, where the atoms are now displaced from their equilibrium positions, which was R and A. So the new position is RNA plus SNA. So if you would like to find the total energy of the crystal inside this configuration, then we can expand the energy about its equilibrium position. So if we do a Taylor series expansion, this would give us the energy when all the atoms are at their equilibrium positions, which is R and A, plus the first order term is 0 because the derivative of U with respect to the displacement has to be 0 because the equilibrium position is gives you a minimum of the energy. So we have to take the second order derivative, and the second order derivative, of course, there's a 1/2 just due to the Taylor series expansion. The double derivative of U with respect to the position coordinates. Now the position coordinates are for that atom with respect to the lattice point are given by partial R N A, and since the displacement could be along X, Y or Z, so we add an additional variable I or J which shows whether you are displacing along X, Y or Z. We need to take the double derivative MBJ. So N and M represent the lattice, the unit cells, the indices of the unit cells. A and B represent what atoms we're talking about, and I or J represent the X, Y or Z direction. So we take this term and we also need to find out the displacements. The displacements are now given by S, the S's. So we multiply this with SNAI, SMBJ, since it's second order, so we have both of these displacements, and we also do a sum, a big sum over all n's, all i's and all i's, all m's, all b's and all j's. So this is the energy in the second order approximation. It's also called the harmonic approximation because this resembles a baseline energy plus half kx square. Okay, the only difference now is that if you have a simple pendulum or a simple mass attached to a spring, you just have half kx square. But now you have atoms that are inside a network that are interacting with one another. So I can model this structure of atoms as many atoms connected with springs. Also have a connection of this kind. And then you can have the same pattern repeated in the third dimension. Right, so there is a complex network of atoms that are interconnected together in 3 dimensions, and motions along x, y, and z are possible, and each atom is interacting with its neighbor. So it's connected through bonds or other kinds of interactions with neighboring atoms. Right? So this is really telling us the strength of the interaction. This term is telling us the strength of the interaction. It's like a spring constant. Its dimensions are of a spring constant, force per unit length. You take the energy, you take the derivative once, you get the dimensions of force, and then you take the derivative again, you get the dimension of force per unit length. So this has the same dimensions as the spring constant, this term. Only that this constant depends upon interaction between two objects, two atoms with their own displacements r n a I, r n m b j. So this is really telling us something about how far apart are those atoms, which is given by the presence of both of these displacements, and how big is the interaction. Okay, so I can also call this term some phi, which is like a spring constant phi, and it's the interaction between NAI and MBJ, and it's directional because of the presence of these I and J terms. Okay, so now this is our energy in the harmonic approximation for atoms that are connected to one another. Okay, now what we would like to do is we would like to write down an equation of motion. The equation of motion, of course, for say the nth atom belonging to the nth unit cell, 8th atom along, say we focus on one dimension I, you multiply this with the mass and take the double derivative of this. This must be equal to a force. Okay, that's the equation of motion. So the force is given by the negative of the derivative of this term with respect to s. So now this really means that I need to find out the gradient of this potential energy U, and since I'm talking about the ith dimension, so I just take the ith component of this. So this would mean, so let's call this the force. The force simply is the negative of the derivative of this. Now this is a constant because this is in equilibrium. The derivative of this with respect to the displacement s will be 0. I need to take the derivative of this object. Okay? So this is of course a constant because this depends upon the strength of the interaction, and I take the derivative of these two terms with respect to, since I'm talking about NAI, So I will just be left with mbj. So this thing will give me minus phi nai mbj s mbj, right? Because the derivative of this with respect to snai is just this term, okay? So my equation of motion becomes ma u n a I double dot. Now I can take this to the other side, plus phi nai. By the way, I also here need all of these sums, nai mbj. So nai mbj s mbj sum over nai mbj, this must equal 0, right? So this is my equation of motion. By the way, I have put this 1/2 factor inside phi. I lumped it together with phi. So now we have an equation of motion, and we need to solve this equation of motion to look at the kinds of oscillations these atoms can have inside the solid. These oscillations are very similar to the normal mode. These are just the normal modes of this large collection of atoms. If there are capital N unit cells, there are R atoms in a basis, there will be R into N atoms and 3 into R into N degrees of freedom of the system. So there will be 3Rn equations of this kind. Now if you notice that we're looking at the displacement of one atom in a unit cell, eighth unit cell, and it really depends upon its interactions with all other atoms, including itself. See, you're taking a sum over all mbj's, correct? So now with this, so these are all pairwise interactions that exist inside the system. Oh, by the way, one thing, sorry, I've there is no sum over nai here, because when I take the derivative of this object, so I really need to take the derivative of u with respect to snai, right? This term is this term. So only that derivative survives for which this term is snai. So I don't take a sum over nai, I just take the sum over mbj, because all other terms vanish. So my equation of motion, all in all, is given here. Okay, you समझ आ रही? So this is my equation of motion. Let me write this again. ma unai double derivative with respect to time, sum over all mbj's, where mbj's are all other atoms inside the system, which might include that very atom as well. The interaction of the naith atom with the mbjth atom multiplied by the displacement of the mbjth atom. So this is my equation of motion. I can solve this. So let's call this equation number 1. So in order to solve this equation, what I could do, I could propose an ansatz. That ansatz is, so suppose my unai is given by some amplitude, sorry, I'm so sorry. This should be S. So sorry. Right, so this is the acceleration of the NAI that this should be an S here. So I assume that my SNAI is some amplitude U AI. Now since all the lattice points are totally equivalent, I can drop the index n. This amplitude will be independent of the index n because all the lattice points are just the same. No matter what n is, since it is by definition a lattice, therefore the displacement of any lattice point is going to be the same. So this is UNAI into some phase. Okay, so you need to add a phase to this, EI. Now that phase is given by some vector Q, wave vector, into the displacement of that particular lattice point Rn minus, of course, there could be some time factor. And by convention, I can normalize this or divide this by the square root of the mass of the eighth atom that we're talking about. So this is our proposed solution. It's called an ansatz. So we take this ansatz and insert it into equation number 1, which is our equation of motion. So if I take the double derivative of this object, the double derivative will give me a minus omega square. So I will be left with MA from here minus omega square MA, correct? UAI, I have intentionally dropped the index n here because this result is independent of which lattice point we're talking about. They're all the same. Okay, so the amplitude is going to be the same. The phase will be different, but the amplitude is going to be the same. UAI EI Q dotted with Rn. I also drop this omega t factor because this term is going to appear with everything, with all terms. So it's common to all terms, plus the sum over all m's, b's and j's, and I have phi NAI MBJ SMBJ. So I will put 1 over m b square root u bj e I q r m, right? So this is now my equation of motion with the ansatz. Is equal to 0. Right? So now what I could do, I could divide both sides by square root MA. This becomes minus omega square U A I. Okay? Under root M, I divide, so this is actually square root MA. I divide by square root MA, this goes away. I will also take this to the other side, so I will get MBJ phi NAI MBJ 1 over MA MB2, right? EI Q dotted with Rm. Since I want to get divide by EIQRN, so I put minus Rn here U M Bj. Now I don't need this M or N. Okay, so this is my equation of motion. So it has been considerably simplified. So what I could also do is, so conventionally I could write this as plus sum over Bj, sum over M. I separate this out, phi NAI MBJ 1 over MA MB EIQ RM minus RN UBJ. Now this term is a summation over M, so it will be independent of M. Right? So since we are summing over all m's, it's independent of M. And since there is translational symmetry, the sum over M takes away the M variable. Correct? Now since this does not depend, so what is this term? This term is the interaction between two atoms in two unit cells, one with index M and N. Right. So Rm is, and Rm minus Rn is the difference in the translation vectors between these unit cells. So I could have two unit cells inside the system, my crystal, right? And this suppose is Rn, this lattice point is Rm. So Rm minus Rn is this displacement, correct? This displacement here, Rm minus Rn. So it really, and there is an atom here, some atom say here A here and some atom B here. So it's really the interaction between these two atoms belonging to two unit cells separated by M and N. Okay, so the result only depends upon how far apart are these unit cells. It does not depend upon what N you take, and it does not depend upon what M you take. It only depends upon how far they are apart. Therefore, this sum is independent of M because we are already summing over all m's, and is independent of the N as well, because you could take this unit cell to be anywhere else, and if it is displaced, and if you're looking at another unit cell which is at the same relative position with respect to this, anywhere inside the crystal structure, this term is going to be the same. So this term is a term of a dynamical matrix. It is independent of M and N. Okay, so this term itself, which I've written in these braces, is denoted by D. Okay, and it only depends upon how far apart are N and M. Okay, so 0, I can write 0 M minus N, or I could write N here and M here, so NA and MJ. It only depends upon how far apart are M and N, and of course it depends upon A and B as well, but this term itself is independent of M and N. It only depends upon their difference. It can depend, no doubt, on Q, right? Because there's a Q over here. So it depends upon the wave vector. Hence, my equation of motion can be written as minus omega square U A I plus B, J, D, M, N, M, A, and B, which can depend upon Q, U, B, J. Right. So this is my equation of motion. So now with this equation of motion, I can look at different kinds of crystal structures. In any case, I would need to find out this dynamical matrix element in order to solve a particular structure. Right? Remember these indices I and J represent the direction or X, Y, Z. A, B, C, etc. represent the atom in the basis, and M and N represent the lattice point. And this lattice point is only relevant to the calculation of the dynamical matrix element. There is no N or M anywhere else. So now two examples are nice to see. If I restrain this problem to 1D, to 1 dimensions, so I get a one-dimensional monoatomic system lattice. So which means that I just have these atoms, all of the same mass, connected to neighboring atoms. Okay, and there's a unit cell displacement A, and everything is in one dimension. So I and J are just along one direction. So for that particular case, and there's just one atom in the basis. So A is just a single thing, just one atom. There's no B. So this D, however, as you will notice, is dependent upon the interaction between atoms. Okay. Now the interaction between these atoms is some kind of spring constant, right? So in reality, the interaction between these two atoms, so this is unit cell N, one atom. So N comma is, I just label it as N. This belongs to unit cell N minus 1, this atom belongs to unit cell N plus 1. So this interaction here, phi N minus 1, is some spring constant K. Could be proportional to K, some kind of strength of this bond. There's going to be the strength of this bond here. So this term is going to be equal to this term, phi N interaction with N plus 1. So when I know the phi's, I can calculate the D's. The D's are given by the sum over all phi's for the different values of M. Correct? And then you, right? So you need the different values of M's, and then in this equation you need to sum over all B's and J's as well. So you take the interactions between one atom and all the other atoms and then multiply it with the appropriate phase factor. Okay. So now if you look at this example here, we need to know what is the value of phi. So the phi is coming from, if you look over there, is coming from the double derivative of the energy. So if you look at any pair of interactions, right, U of a pair, so let's find U of a pair. Let's look at the N and the N minus 1th pair. Okay. So let's look at this interaction. If I were to write this interaction in the harmonic approximation, it will look like half K, and this would become the displacement of this atom. Okay. So let's call this R of, this is n plus nth, the displacement of this atom R n minus 1. So the distance between these atoms is this, correct? Take the square of this. But this atom is also connected to this atom. So my focus right now is on the nth unit cell, this atom in the nth unit cell. So it's connected with its neighboring atom. So the total energy that this system sees is, with these three atoms in place, with my pivot on this central atom, is this is the potential energy associated with this interaction. So n is this, m is n minus 1, and another m is n plus 1. There is of course an m equals n as well. So I really need to consider these three atoms together. So the energy associated with this combination is this, and then I need to add to this the pair n plus 1, right? This will give me plus half k. Now I look at this atom, this one, it is at a distance Rn plus 1 minus Rn whole square, right? So this is my energy. Now if I need to find out the phi's, I need to kind of differentiate. How do I differentiate? I differentiate with respect to Rnai and Rmbj. Okay. Now how many phi's do I need? I need to find out, if I need to find out these d's, I need to find out the phi's. My other assumption is that only nearest neighbor interactions exist. So this atom is connected to its neighboring two. So I need to find out three kinds of spring constants. I need to find phi n n. I need to find phi n minus 1. I need to find phi n plus 1. So this interaction is this energy, let's call this energy T, okay? T is not a good name, it's represent kinetic energy. Let's call this energy V. So I take the double derivative of V with respect to Rn, because both of these indices are the same. So when I take the double derivative of this, I will get 2k. This term will be partial square V partial Rn minus 1. So when I differentiate this V with respect to these variables, I'll get minus k. Here partial square V partial Rn plus 1 minus k again. So these will help me find out the d's. Now I put everything inside that equation of motion. I have minus omega square u. Now I don't need to write out a and I, because a is just 1, I is just 1. Minus omega square u. U is the amplitude without the phase of any atom. Plus. Now I need to find a sum over b's and j's. Okay, so I really need to find d B is just 1, J is just 1, okay, but D itself is the sum of these phi's, correct? So this will give me plus phi. Now the variable that I need to iterate is over m in the calculation of D. So I have phi n, correct? First I take this m equals n, okay. Now this term will be Rm minus Rm is 0, this will be 1. I will get 1 over, all the masses are the same, so I'll get 1 over m square under root 1 over m. So just put 1 over m plus the next term for the next value of m. So the next value of m, okay, I don't need this, the summation over b over j, because there is only one b over j. So I just, for each b over j, which is just 1, I take these 3 m's plus phi n. The next value of m is m minus 1, still the same m over here, plus phi n plus 1 u equals 0. Okay, so this is my equation of motion, and I've already know the relative strengths of these interactions. So I get minus omega square u plus 1 over m. But do remember, don't forget the exponent factors here. So here I have exponent, some exponent here. What is that exponent? It's Rm minus Rn. So it's minus IQA. Correct? Rm minus Rn. The separation between Rn and Rn is by unit vector A. So Q dotted with A is QA. So minus IQA, and here I get a factor E plus IQA. Okay, so this term is 2k plus, in fact, minus this minus here, k into the sum of these terms, which is 2 times cosine of QA, u equals 0. So this would result in minus omega square plus 1 over m 4 k sine square QA over 2 u is 0. Now u cannot be 0 because otherwise there will be no oscillations. So this means that my omega is related to q, which is the wave vector of the oscillating wave. Now we'll see what is that oscillating wave. Okay, so this omega square therefore is 4k over m sine square QA over 2. If I were to make a plot between QA okay and omega square, I can take the square root of this. So the square root omega is 4k over m under root sine of QA over 2. Right, so this is omega. So if I make a plot between omega and q into a at 0 q, which is the wave vector 0, which means infinitely long wavelength, a long wavelength wave is trying to pass through this one-dimensional solid, the frequency is 0. And this goes up, yes, the sine function on both sides as well. QA could be positive or negative. You could have a wave traveling in one direction or the other. And then it repeats itself. So when this becomes, QA becomes pi, if I were to plot Q with respect to Q, let's plot with respect to Q. So this Q becomes pi over A. When this Q is pi over A, this is maximum. This is minus pi over A, it's maximum, with a value given by 4k over m. Okay, and then it repeats itself. But the period is 2 pi over A. So this expression of omega as a function of Q is called the dispersion relationship. It's periodic in 2 pi over A, and 2 pi over A is the length of the reciprocal lattice vector. So this omega really has a period of G, where G is the length of the reciprocal lattice. And it's also an even function with respect to Q. And that's because it's the equation of motion obeys time reversal symmetry. Alright, so it's sufficient to kind of just show this dispersion relationship in the region between minus pi over A to pi over A. In fact, just between 0 and pi over A, because of these two properties. I can also immediately show that this equation of motion that I've written in pink over there is independent of, if I do a translation in the reciprocal space by G, that equation does not change. Because if I put in that equation if I were to put minus omega square u now let's put back 3D notation uq plus bj d n a m p q, and then I have u p j j I. If in this equation, which is 0, if I replace q with q plus g or minus g, what will it change? It will just change this term. This q will be replaced with q plus g. But I know that eig into any translation vector in the lattice space is ei 2 pi and some multiple of it, which is 1. So replacing this q with q plus g, q plus 2g, q plus 3g does not alter anything. Therefore, this dispersion relationship is periodic with the period equal to the length of the reciprocal lattice vector. And we'll see later that this region of this wave vector is called the first Brillouin zone. It extends from minus pi over A to 2 pi over A. So and its length is 2 pi over A. And we'll see how to construct these zones. So if I were now to kind of shift gears a little bit and make this problem a bit more advanced and look at a 1D diatomic lattice. Now in a 1D diatomic lattice, there are two kinds of atoms. So the basis will now have A and a B. And if I were to depict this situation, two atoms, and they could have different masses, say MA and MB. And I also assume that these spring constants, these interactions are the same, K. And this is my unit vector now A in the real space. Now what I could do is I could write down the equation of motion. Now I have two kinds of A and B's, right? But still one dimensional. So the equations of motion will now, there will be two equations of motion. Okay? Because there are two atoms, R is now 2. Okay? So I can write minus omega square UA for the Ath atom, plus I can write, now I need to sum over, so I have UA and UB, so I will write D M N A UA plus D M A N B UB is 0. Correct? So this is one equation, and the other equation is minus omega square UB plus DMB, sorry, उधर हम m ही लिखना, ठीक है, DMB NA UA DMA plus DMB NB UB. So here are my two equations, right? And we need to find out the dynamical matrix elements corresponding to these. Okay, so now I do know that each of these atoms is once again connected to neighboring atoms. And if this is my nth unit cell, this will be my n minus 1th unit cell, this would be my n plus 1th unit cell. Okay. So if I focus my attention on here, right, I will get, so these D's will depend upon the phi's. So I can write down these D's. TMA, एक मिनट मैंने जरा उल्टा लिख दिया है, सॉरी. This is DNA, DNA, DN, DN, N, 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 M. Okay. Now M could be n or n minus 1 or n plus 1 as before. Okay. Now let's look, there are 4 kinds, right? there are 4 kinds of Ds. So if I were to take D, N, A, M, A and sum over M's, right? So D, N, A, D, M, A is this term. Now I need to sum over all the M. So in order to calculate this term, I need to sum over M. So slightly complicated. So it's phi NA plus phi. So this is it. So an nth atom is just eighth atom is just connected to an eighth atom. There is no eighth atom connected. There is only one kind of AA connection, that is with itself. So this is phi NA over MA square under root, which is MA. Okay. This we already know is of this kind, 2K. Correct? Now the second term DNA MB over there is, now an A atom is connected with the B atom. So this can be in 2 different ways. An A atom can be connected with the Bth atom in the previous unit cell or in the same unit cell. Okay, so if it's connected with an atom in the previous unit cell, you see here I'm looking at an 8th atom. This is my 8th atom. It's either connected with the B atom in the previous cell or in the same cell. So if I look at the previous cell, so I will get F phi Na n minus 1b, right? Divide by, now there are 2 different kinds of atoms, so Ma, Mb under root. And there is also a phase factor now, because now I have moved across unit cells. And that phase factor, what is the distance between the n and the nth minus 1 lattice point? The corresponding lattice point is minus a. Not the atoms, but the lattice points is minus a. So I have minus I QA plus inside the same cell. So now I'm considering Na. This M is still N, but the Bth atom. And again, there are 2 different kinds of atoms. So Ma, Mb under root. Since it's in the same cell, I'll get a 1 over here. It's in the same unit cell. So I have written down found out all the terms in the first, in equation number 1. So if I write it down, equation number 1 becomes minus omega square UA plus 2K over MA over MA plus, now this is minus K, this is also minus K MA MB E minus IQA, this is again minus K MA MB, right? And all of this comes with the UA and this comes with a UB. equals 0. Right? So likewise, I can find out the terms pertaining equation number 2. All in all, I will get a relationship of this kind: minus omega square plus 2k over ma minus k ma mb 1 plus e minus qa minus k ma mb 1 plus e minus iqa minus omega square plus 2k over mb u1 ua ub equals 0. So this is my dynamical matrix over here. Now in order to solve this, solutions will exist when the determinant of this thing is 0. Correct? So I can now find out this determinant. Let's move to that part of the blackboard. Is it clear? I've gone really slow and systematic here. So if I find out the determinant, this becomes omega 4 minus omega square two k over ma. One over ma plus 1 over mb plus 4k square MAMB 4k square MAMB minus 4 AC 4 sorry minus k square MAMB k square MAMB, and then I have 1 minus and then 2 4 cosine square Q QA. So QA. Right? Minus 4 cosine square, sorry, cosine QA, cosine QA. Yeah. One plus cosine QA क्या हो गया ठहरो, उसको मल्टीप्लाई किया प्लस 4 के इसमें 2 1 plus cosine QA. This is cosine square QA over 2. This is our result. Now if you look at this result over here, let me also turn on our laptop. So I've just found out the determinant of that matrix. So if you look at this result, this is omega 4 minus omega square 2k 1 over ma plus mb plus 4k square over MA MB. This, remember, is 2 cosine square QA over 2. 1 minus cosine square QA becomes sine square QA over 2. So this becomes sine square QA over 2. This equals 0. Now I can find the roots of this. So this is a quadratic equation. I can solve it and find the roots. Okay. How many roots exist? So for a given q, there will be 2 roots. It's a quadratic equation in omega square. So if I were to plot, I put q here and I plot, say, omega, which is omega square, which is the solution to this square root, and then take only the positive square root. Let's see what this plot looks like. In order to look at the plot, so what I've done is I have taken the solution to this. Omega square is 2k 1 over MA plus 1 over MB plus minus this square 4k square 1 over MA plus 1 over MB square minus 4 into this, all of this, 4k square MA MB sine square QA over 2. Okay, I have taken this omega square. Okay, and then I take the square root of all of this to find out the omegas. Now there are 2 solutions, one corresponding to positive root and the other corresponding to the negative root. And another thing, in order to plot this, what I've done, I've taken all of these to be 1. So everything that I put in squares is 1. This is 1 unit, 1 unit. A is 1 unit. Okay, A is 1 unit. Got it? So now I vary my MB. It could be, suppose it's something less than 1, something less than MA. So I vary it from 0 to 1. Okay, and I call this MA X. Sorry, this MB is X. MB is X in my plot over there. So if my X is 1/2, so one atom is twice heavier than the other. So when I plot the results, this is what I get. Okay, if I make this even lighter, this is what the plot looks like. So the gap between the upper branch and the lower branch increases. So these are branches. 2 atoms in the basis, I get 2 branches in one dimensions. If there are 3 atoms, I will get 3 branches. 4 atoms, 4 branches. If X is very close to 1, 9 over 10 say, these gaps decrease, right? So what this really shows is, one thing you also notice, again there is periodicity. So this is Q, Okay. So, and this point is about equal to pi. Is about pi. I do know that I have, this is should be pi over a. A is 1, so this is pi, this is minus pi. So again there is this periodicity of 2 pi over a. And there are two branches. Okay. So, and you also notice that I can also plot this all together. Populate. You see now x is 0.1, I increase the value of x, which means the two masses are becoming almost the same. And this is how the band gap, so this is like a band gap, this is a gap between two branches, this is decreasing. So again you see the periodicity, you see probably two Brillouin zones here over here, okay. And these branches, now this branch starts when q is 0, omega is 0. And if you look at the solution here, if you put q equals 0 here, this becomes 0, right? This becomes with the minus sign, this becomes 0, so omega becomes 0. And this becomes 2 times this with the square root, okay. So this is one point here, q equals 0, and the blue one is at another point. Okay. So you see this point here and this point here, both of them correspond to the two branches. Now if this branch, lower branch, is called the acoustic branch. And these are historical names. It's called the acoustic branch because if you look at sound has omega which is directly proportional to k, like any wave. You see, you know, f equals v into lambda. You take the inverse, you get omega equals vk. So in this low q region, when q is low, sine square qa over 2 can be represented by q square a square over 2. This becomes small, and this you take the under root, so this becomes a linear relationship. In this region, this is like a linear relationship between omega and q for the low q, long wavelength regime, and it's very similar to sound waves. That's a dispersion relationship for sound waves. So that's why this branch is called the acoustic branch. Okay. That branch is called the optical branch. Okay, and there is a reason why it is called the optical branch. It's called the optical branch because this is probably a homework problem, that if I put q equals 0 or small q, and then I find out my omega, and then I put my omega in here into this relationship and find out what my UA and UB are, I'll get the amplitudes. I can get the relative sizes of the amplitudes. For the acoustic branch, which means when I take into account a negative sign in the square root, for the acoustic branch, UA and UB, both of them are in the same direction, which means UA or UB is positive, which means that one atom I have one atom here. So this is the amplitude of UA, positive, this is also positive. So when this is negative, this will also be negative. Their amplitudes can be different in size. Their masses are different, so they're different in size, but they all move together. So this atom moves to the right, this atom moves to the right. At these in this long wavelength regime, when Q is small. And this is called an acoustic branch, an acoustic oscillation. In the optical oscillation, UA and UB, if you put this value of omega here into that equation and look at the ratio of UA and UB, they will be negative. The ratio will be negative, which means that if this atom moves to the right, the neighboring atom moves to the left. If this atom moves to the left, this atom will move to the right. So, whereas the centers of mass might also change because the masses are different, but one is moving to the right, the other is moving to the left, right? So they are like breathing like this. Oh, sorry, this goes here. Yeah, they are breathing like this. Okay. It's called an optical mode because if this were an ionic solid, there was some positive charge here and some negative charge here. This is an electric dipole moment. And when the length of this electric dipole moment oscillates, right, it's oscillating, which means the polarization is changing, which means it can absorb optical radiation of optical wavelengths at optical frequencies, especially in the infrared regime. That's why it's called an optical mode. So there's an acoustic branch and there is an optical branch. Still you see the periodicity of the Brillouin lattice of the reciprocal space. Still you see that it's an even function. Okay. Now we will extend this concept to three-dimensional solids and look at the kind of nomenclature that exists. And we will also kind of quantize all of this to introduce the idea of phonons. Okay, thank you very much.